Welcome to Calculus. Today we will investigate how to integrate indefinite integrals by parts. We'll take a look at 4 examples. Our first example is the indefinite integral of x times e to the power of x dx. We want to integrate this using the strategy of integration by parts. And what that really comes from is the product rule of differentiation. Let's give the definition about how we integrate by parts. So if I've got this function u times v, and I want to take the derivative of that function, what we would do is we would place a ddx, and we know the product rule. It would be u times dv dx plus v times du dx. Now, to arrive at the rule that we would use for integrating by parts, I would integrate both sides of this product rule. So I'd integrate that left side, and I'd also integrate this right side. And then what we want to do is solve at that point, simplify. So on this left side, this integration of the derivative of u times v is going to be just u times v. And on the right side, we'd have the integration of u, and I'm going to reduce this down to just say that's dv, plus the integration of v du. Now, to arrive at the integration by parts rule, I do want to move one of these terms. And the one that I want to move is this integration of v du. So I'm going to subtract that over. And with that subtraction, we've arrived at a rule that we can use here. So let's put it in an equation form. So then the integration of u times dv is going to equal u times v minus the integration of v times du. And that's exactly what we're going to use for this process of integration by parts. So I want to start on this left side of the equation, and really what I want to do first is identify which factor in my integrand is going to be associated with the u and which factor is going to be associated with the dv. Now, we have a few guidelines. I want dv to be the most complicated part of the integrand that fits a basic integration rule. So I'm looking here at my integrand x e to the power of x, and that piece that I want to call dv is going to be e to the power of x dx. And as a general rule of thumb, the dx is always going to be a part of dv. And that leaves for me x, which I'll identify as u. And as a general rule of thumb, you want u to be the portion of the integrand whose derivative is a function that's simpler than the original one. So derivative of x is just 1. That's simpler than x. So once I've got these pieces identified, which essentially it's a guess at first, I want to then bring them over to the side, and in one case integrate, in one case differentiate. So dv, if that's e to the x dx, then definitely I want to integrate that to arrive back at just v function. So the integration of e to the x dx is just going to be e to the x. And definitely it's a good check at that point to see whether you've chosen a good factor from your integrand to identify as dv. It should be integrable pretty easily. We also called our u simply x. So in that case, I want to differentiate. Du is going to be just 1 times dx, or just dx. Now, once I've got that identified, I'm now shifting my attention from the left side of this equation over to the right side. Notice I have definitions for all these factors for u, v, and du. So let's fill in. I'll write it here just so we can see it. So the integration of u dv is going to be equal to u times v minus the integration of v du. And at this point, we're making substitutions. So my u was just x. My v is e to the power of x. And then I want to subtract the integration of v, which is e to the x, times du, which is dx. And that integrates, in this example, very simply. Integration of e to the x dx is just e to the x. So this would reduce down to just x, e to the x, minus e to the power of x as the integration of that, e to the power of x dx plus c. And that completes the integration of that first example. So in this example, it's pretty easy to see which piece we should identify with dv, which piece we should identify with u. Let's take a look at another example. Here we've got the integration of t times the natural log of t plus 1 dt. So again, I want to start off by identifying which part is going to be my u, which part is going to be my dv. And recall, we have those general rules of thumb. So just again, I want dv to be the most complicated part of the integrand that fits a basic integration rule. So my dv, the temptation is to say here that it's going to be the natural log portion. But in fact, I want to save that natural log for the u. For the very simple reason that it's easier to take the derivative of natural log than it is to take the integral. So in that case, I'm going to call my dv t dt. So let's set that up. Again, over on the side, I'm going to take dv, and that's, again, t dt. And that part I want to integrate to get just the function v. So for us, that's going to be 1/2 t squared. Then I'll bring my other part, my other factor, u, which is the natural log of t plus 1. And in this instance, I want to differentiate. So du for us is going to be 1 over t plus 1. By the chain rule, there's going to be nothing left when I take derivative of t plus 1, so we're good on coefficients, dt. So that's ready to set up. Let's remember our rule again. It's the integration of u dv equals u times v minus the integration of v du. So again, I just want to substitute parts in here. So now it's going to be equal to u times v. So that's the natural log of t plus 1 times 1/2 t squared. That was my v. Minus the integration of v, which is again 1/2 t squared, times du, which is 1 over t plus 1 dt. So at this point, I need to really bring my attention to the second term here, the integral. I'm going to write it as one fraction. So it's the integration of 1 times t squared. In fact, what I can call that is just t squared over, I'm going to let that half go in the denominator, so 2. In fact, instead of letting that go there, I'm going to pull it to the left on the outside of the integration. And what that'll leave below is just t plus 1 dt. Now, in order to integrate this rational expression where the power is higher above than it is below, I need to employ a strategy from algebra. I need to do long division to simplify that fraction. So over on the side, Again, this is just an algebraic strategy to simplify the integration. I'm going to take and divide t squared by t plus 1. So I'll do polynomial long division here. I need a placeholder for the linear term, so plus 0t, and a placeholder for the constant, so there's another 0. So we'll divide. Recall you start with your first term, so t squared divided by t is going to be just t to the power of 1. So I'm going to put that quotient there, t, and then I need to multiply back. So t times t plus 1 is going to be t squared plus 1t. And then I want to subtract. It'll cancel my first terms, and this minus is going to distribute. So 0t minus t, so negative 1t, carry down my 0. Now I'm going to divide negative 1t by t, and that gives me minus 1. Carry that up, multiply it back, so that's negative 1t minus 1. And that I'm going to subtract, so the first terms cancel. The negative distributes to the negative that's there and becomes positive 1. So I'm going to write this fraction, t squared over t plus 1, as this now polynomial. It's t minus 1 plus 1, that's my remainder, divided by the original divisor t plus 1. And that's what I want to integrate. That's going to be simpler than the original fraction where the power was higher in the numerator than in the denominator. So again, I'm going to bring back the pieces that we kind of left behind. Let's change the order here in this first group of terms. So it's half t squared times natural log of t plus 1. And then we'll pick up. So we're ready to integrate that second term there. I'm just going to fill in the gaps. All right, so again, we'll pick up our pieces, half t squared times natural log of t plus 1. And now we're ready to integrate this second one. So minus half, and then we're going to integrate t. That's going to be 1/2 t squared. Minus 1 will integrate as minus t. And then 1 over t plus 1 is going to be the natural log of absolute value t plus 1. And we'll close that out. We're getting very, very close to our other work there. So let me draw a red line to kind of separate. And then the last piece we need to catch in here is the plus c. So that's all kind of spread out. Right now, we just need to simplify it down. So we'll write this first term again, half t squared times natural log of t plus 1. And then I want to write minus half times, well, in fact, let me go ahead and distribute. Go ahead and start that. So I'm just going to multiply negative half times each term in this green integrated part. So it's negative half times half is minus 1/4 t squared. Negative half times negative t's plus half t. Negative half times natural log of t plus 1 is minus half. ln absolute value t plus 1 plus c. And that's our final answer. It's crocodile long, but it's complete. So with that example, we did use a number of strategies. Really, the main ones there are going to be the integration by parts, but also polynomial long division to make that fraction integrable. Our third example looks very complicated. So here we've got the integration of x e to the power of 2x over quantity 2x plus 1 squared dx. So it's a real puzzle to try to choose which factor here is going to be my dv and which factor is going to be my u. So we'll just go ahead and kind of split the fraction. Let's call this numerator factor x e to the power of 2x. We'll call that our u. And then what is left is going to be this denominator of 2x plus 1 quantity squared dx. That will be my dv. So let's bring them over to the side as we've been doing. So dv again is going to be 1 over 2x plus 1 squared dx. So now we want to integrate to find just v. And to integrate that, really we probably need to make a substitution. So what I'll do here is we got to kind of do a side step. I'm going to call this 1 over u squared, which is really equivalent to u to the power of -2. And then let me back up just a moment. Let my thoughts get ahead of my pen. So let's call u here. And I'm keeping that distinct from my other u. So let's call it u sub 1 is going to be that 2x plus 1. So then du sub 1 is going to be just 2 dx. So that's going to match pretty well when I do the substitution here in a moment. I do need to put a factor of 1/2 because I don't have a multiplier 2 in the numerator there. So for this integration, I'm really going to be integrating u to the power of -2 du. And I need that half out front. So just integrating there with that simpler version, that's going to become, if I add 1, -1, u to the power of -1. And at that point, I can get rid of my integration and put back my 2x plus 1. So this is -1 over 2. And then because it's to the power of -1, I'll let it go to the denominator and assume a positive power of 1. So all that was to get my v here. So that's going to be -1 over 2 times 2x plus 1. So that took a little doing, but it's possible to do, and we did it. So let's just pick up our u then. That's going to be x times e to the power of 2x. And that I want to differentiate, which is not bad to do because that's just a product. So I'm going to use my product rule to catch my du. So it's going to be x times the derivative of e to the power of 2x, which is going to be itself 2 e to the power of 2x. And I need that 2 according to the chain rule. It's the derivative of the 2x in the numerator plus e to the power of 2x times the derivative of x, which is just 1 or dx. So that is ready. Put brackets and get our dx in there. So let's set it up according to the definition for integration by parts. So if I'm integrating u dv, again, by our rule, that's going to be equal to u times v minus the integration of v du. So then I'm going to just substitute in. My u again is 2x plus 1. Oh, I'm grabbing the wrong u. U is x times e to the power of 2x minus the integration of v. So that's -1 over 2 times 2x plus 1. And then du was a longer expression. It's 2x e to the power of 2x plus e to the power of 2x dx. So that's looking very complicated in my second integrand there. But one thing I can do is to simplify it algebraically. So I just want to do some work there. I know that this second binomial is going to go into the numerator when I multiply it in. So I think I want to try to create a cancellation. So I see I've got e to the power of 2x as a factor of both terms in the binomial. So I'm going to factor it to the left. What that's going to leave me is 2x from the first factorization plus 1. Now, keeping in view how that's going to help, that's going to make this the integration of negative. I'm going to let this green version multiply times 1 in the numerator. So e to the power of 2x times 2x plus 1. And then let me just bring back what was already in the denominator, 2 times 2x plus 1. And lo and behold, we've got a cancellation that's really going to make this integration a lot simpler. So I'm going to bring back my other pieces here. So I'll bring back the x, e to the power of 2x, and the minus. And let's pick up right there. So this is now going to be equivalent to, we can probably drop our parentheses, x times e to the power of 2x. My negatives are going to become plus. I'm going to let that 2 come out as a half times the integration. All that's left is e to the power of 2x dx. So I do want to do the substitution here for that power of 2x. So I'm going to call that, we got lots of u's flying around. This is u sub 2 to be distinct from u, and u sub 1. That's 2x. So du sub 2 is going to be just 2 dx. So I got the dx there. I do not have a 2, so I want to include something to cancel it, which is going to be a factor of half on both sides. So as I complete this integration, it's going to be, I'll do this integration part first, half times the half for the scaling with the substitution, and then e to the power of 2x. Bring back my first term, x e to the power of 2x, and plus in between them, and that really simplifies down to x e to the power of 2x plus 1 over 4 e to the power of 2x plus c. And that completes integration for that apparently complicated example, but not too bad when we applied our rule. Before we move on, I see that I've left out a part of the solution here, the piece that I did not include. I mean, it just shows it's easy to drop factors here in the process. I didn't include the v. So what I need to do is I need to reincorporate that just to identify what's my v. It's the negative 1 over 2 times 2x plus 1. That needs to go as a factor by all these terms. I just left it out. So what I'm going to do is I'm just going to drop it in to that last one. So I'll just write v, 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 v. And for the last one, basically what we can do is just put the parts around it. So it's negative 1 over 2 times 2x plus 1. So we can fit that in, place negative on the 2x plus 1. And that helps us out here. So I'm going to put it in the last version of this example just by putting a denominator, negative 2 times 2x plus 1. So it's important to look back and make sure all the details are in order. And we're good now with that last adjustment. Let's take a look at one final example that involves just a single factor in my integrand. So a lot of times when we do integration by parts, we really are expecting to have multiple factors so that I can identify one piece as u, one piece as dv. But here I just have one. So I've got the inverse tangent of x and dx. So if I'm going to use integration by parts, I'm going to call this inverse tangent of x my u. And dv, I'm going to identify as dx. So we'll approach it just like we've done in our first three examples. So I need to integrate here. So v is going to be just x. And then for my u, that's going to be the inverse tangent. And that I need to differentiate. And that's going to be 1 over 1 plus x squared dx. So we'll set that up according to our definition for integration by parts. So if I'm integrating u dv, that equals u times v minus the integration of v du. So as in our previous examples, I just want to start substituting in what I've determined here already. So u is the inverse tangent of x. V is just x minus the integration of v, which is x, times du, and I'm just putting the x in the numerator, denominator 1 plus x squared dx. So I see in my integration part now with this integration by parts, I've got 1 plus x squared in the denominator, and I've got x in the numerator. So my strategy there is going to be to treat that as a substitution. So what I want to substitute, I want to call, and we'll call this u sub 1 like we did in a previous example here. U sub 1 is going to be 1 plus x squared. Du sub 1 is going to be 2x dx. And so what I see here is I've got my x and my dx, and I've got my u sub 1. So all I need to take into account is this 2. I don't need it there, so I need to cancel it with a half. And let's make our substitution. So now I'll just focus on this integration part. We'll bring down the inverse tangent of x times x in a moment. So bring the integration. And this is going to be equivalent to, I'll put that half outside, the red half, 1 over u du. And that's going to be easily integrable as the natural log of u. Let's bring back our other parts. So I'll bring back the inverse tangent of x times x. And then let's resubstitute back in what we were calling u sub 1. In fact, I should mark those. We'll also put plus c. So here's our simplified version. So inverse tangent of x times x minus half times natural log of u again is 1 plus x squared plus c. And that finalizes that integration. Thank you for joining for this investigation of how to integrate indefinite integrals by parts. See you soon.